Now let's try to solve the problem with the method we used yesterday. Why the old method break does not work. If you write the matrix, remember the second equation is like this, equals 640. As I pointed out, the canonical form needs everything like this base variable to be positive 1 and the rest all 0. You're going to have a negative 1 for this s. That s is not going to be a base variable, and you don't have a solution immediately. Since the method break, we tune a little bit by adding another variable, a1. This variable, we call it the surplus variable because you have more than you need. So instead of just minus s, we plus this a1 called the surplus variable. And also introduce an artificial objective function called the AF equal A1. So besides your original objective function here, we write down, we introduce another variable AF in the last row of the table, and the equal A1. See, this is A1 equal A1. That's how you start. But this initial table is not the canonical form we talked yesterday. Why? Because this A1, you have 1 here, 1 here. The A1 is neither a base variable. A base variable always need to be something like that. You have 2 of the 1. So step 1 is obvious. I want to make this A1 as a base variable by subtract this last row, 1, 2, 3, 4, 5, 6. The row 6 minus the second row, I make this row 6 as 0. Then now after this subtraction, you see the A1 is good. It's a base variable. S1 is a base variable. S4 is a base variable. S1 is good. That's not good. This is not. OK. Now you get a canonical form. Why? See, you get all this right block as unity vectors. Now, step 1. You do exactly what you did in last lesson. Identify one negative number, the smallest one. And since here type of negative 1, you can randomly choose, but the best choice is the x, because the second is negative 1.4. So it's good to choose the first one. And then we get our critical column. And we go do the dividing of the positive number to find the critical row. 2000 divided by 1, too big. 640, that's probably the smallest one. If you look at the ratio, and so 640, that's 800, that's 1440. So the pivot element is going to be this one. The x is the enter base variable. And look at here, the A1 is going to be the leave base variable. So what's the next step? You want to make this x column be a base column. Means this is 1, that must be 0, 0, 0, 0, 0. That's our goal. We use the Gauss-Jordan algorithm, subtract. So that's the analysis I talked. OK. Now, once I make this as a base variable, you can see we are good in the last row. there's no more negative, then the halting condition is true. So we finished the first phase. That's the end. Now there's no more use for this artificial objective function. And there's no more use for this surplus variable. I don't need it anymore. And you can see we made the progress. From the original 19,000, now we got 18,000. Down. We move it a little bit down. The second phase starts at a new table by removing the last row and the artificial column. And here it is. So we get this F minus 18,224. That's just the calculation. You follow. Okay. Now we select the pivotal column. That's the nth base variable, which is S2 for this row. And we divide. That is the smallest one. We find that the leaving base variable is the S2. So the next step, do the same thing. We want to make this pivotal element be 1, and then 0 here, 0 here, 0 here. Oh, no. 0 here, and only 1 here. So that's the goal for next step. That's 1. Well, let's finish this step to see what's going on. That's the same method as we talked in last lesson. Okay, now S2 is a base variable. See the 0, 0, 1, 0. And what's wrong here? Oh, Y2 is still wrong. It's a negative. You remember the halting condition, you need all positive. This is negative. So Y will become the new nth base variable. And we divide all the positive one. That's 1200. That is infinity. That does not count because it's negative. That's 1400. So this is smaller. That's the, we call it pivot element. So you go across, the S1 looks like the leaving base variable. And then the next round, what you're going to do is keep this one and make this 0, 0, 0, 0, and see what's happening. All right. I think that's a typo. That's a 0. So the y and x both become base variable. That means it matters in the solution. Of course, that's the, we call it design variable. That's also a signal if you get the right answer or not. And the S4 is a base variable. S2 is a base variable, not S1, not S3. Now the halting condition is true. You can halt. We finished. So what that mean? That tell you the x equal 800 and the y equal 1200 and the U of F is 16,800. In cents, that's $168. The same solution as we got from the graphic method. So in the whole procedure, we have a lot of detail. At this stage, you may be not quite grasped yet, has not quite grasped yet. Focus on the key point. The key point, what make it wrong for the previous method is you got this lower limit. Since you got the lower limit, and when you introduce the select variable, you got the negative here. That won't give you the canonical form of the method yesterday. So the idea to work around this is introduce an artificial objective function in the last row and add as a plus variable here, a1. And then you write all the equation into matrix form and build this initial table. That initial table is not a canonical, and then you make it a canonical. Once you make it as a canonical, then you start to phase 1 to make a holding condition be true. And then you do the phase 2 after you get rid of the artificial objective function and the plus variable. Once this becomes true, you take it away and start from the phase 2. So that's when the phase 1 stop, phase 2 start. So in the previous example, I skipped all the details how I used the Gauss-Jordan algorithm to switch in the base variables.